When RAG fails, the model may not be the problem. RAGAS helps measure whether retrieval found the right context before you blame generation. After this, you'll understand how to assemble a pipeline that scores retrieved context and separates retrieval misses from answer writing failures. I'm Professor Pi, teaching search and IR with simple Python. Retrieval is the first domino in any RAG pipeline. If the retriever misses the evidence, the LLM can only guess. RAGAS gives us a way to score retrieval on its own, so we stop guessing about whether to tweak the model or the search layer. This matters in products where one wrong answer can mean the difference between a quick fix and a full retriever rebuild. RAGAS treats retrieval like a per-chunk yes-no. Did the retriever return each needed chunk? And how much unrelated material did it bring back? The two signals are recall, which finds missing evidence, and precision, which exposes noisy context. Together, they tell you whether to widen retrieval, re-rank results, or limit how much context the model sees. We'll build a tiny, clear evaluation pipeline. Create a small sample that records retrieved IDs and reference IDs. Score precision and recall. Then run a mini-suite to decide whether retrieval or generation is at fault. That keeps debugging focused and repeatable. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Let's build the smallest evaluation item that holds retrieved IDs and reference IDs, so we can inspect retrieval directly. This snippet creates the smallest RAGAS evaluation item for retrieval scoring. When a RAG answer is wrong, the first thing to capture is what the retriever returned and what evidence should have been returned. SingleTurnSample keeps those two lists side by side with retrieved context IDs and reference context IDs, so the evaluation can focus on retrieval before judging generation. Here, the toy query returned billing and pricing chunks, while the reference set says billing and security were needed. The visible output confirms the sample has two retrieved contexts ready for RAGAS metrics. Next, we need a way to tell how clean the retrieved set is so we can spot distractors. This example uses RAGAS IDBasedContextPrecision to check how much irrelevant material slipped into the retrieved context. Precision is the retrieval cleanliness signal. If it drops, the generator may be reading distractors, even when the answerable evidence is present. The metric compares sample.retrieved context IDs with sample.reference context IDs through the documented SingleTurn ascore call, and asyncio.run lets this normal Python script execute the async scorer. In this case, only one of the two retrieved IDs is actually in the reference set. The visible score shows the retriever is bringing back useful evidence, but also noise. We also need a signal that tells us whether required evidence was missing entirely. This code uses RAGAS ID-based-context-recall to detect missing evidence in the same evaluation item. Recall answers a different question from precision. Did the retriever find the contexts needed to support the expected answer? The recall scorer looks at the reference context IDs and checks how many of those IDs appear in retrieved context IDs. That makes it a strong first split between retrieval failure and generation failure, because low recall means the generator may never have seen enough evidence. The visible score shows that half of the required context was missed. Sometimes pulling a larger window helps, so we'll widen the retrieved set and measure the change. This snippet widens the retrieved set and uses RAGAS to measure the trade-off directly. In retrieval systems, increasing how much context you pass can recover missing evidence, but it can also add distractors that hurt downstream generation. Wide underscore adds the missing security chunk while keeping pricing as an extra context. Then the same recall and precision scorers evaluate the change. The key idea is not that wider is always better. It is that the effect is measurable before you blame the LLM. The visible output shows recall improved, while precision stayed imperfect. Finally, we'll wrap this into a tiny baseline so one query doesn't mislead us. This example turns the single RAGAS check into a tiny retrieval evaluation baseline. One query can be misleading, so cases holds multiple SingleTurnSample items and scores each with the same IDBasedContextPrecision and IDBasedContextRecall objects. The loop keeps the evaluation path small. Score precision, score recall, store the row, then summarize the suite. The status rule is intentionally simple for teaching. In a real system, you would tune thresholds against product risk and review examples. The visible output shows average recall is still below the bar, so investigation should start with retrieval rather than generation. In a real project, you would run this baseline across your user queries, inspect low recall items manually, and prioritize changes that raise recall without destroying precision. That targeted feedback loop speeds up practical fixes. It's a small pipeline that compares retrieved context IDs to reference context IDs to tell retrieval errors from generation errors. Use it whenever a RAG answer looks wrong and you want to know if the model ever saw the evidence. One caveat: high recall with low precision can still confuse generation, so balance the two metrics against your product risk. To move this forward, increase the number of retrieved chunks per query, and rerun the suite to see how recall and precision change. Then pick a retrieval window that meets your product threshold. If practical IR help matters, subscribe and watch the IR videos.